Well, welcome back to our course on system engineering. We're continuing now our working through the second section on design and integration. This is where we get into a lot of the heavy lifting in terms of how we develop a design. And then we then transition from doing the design to the integration and test. And so we just finished up with the couple steps here in terms of the design development. You have the functional architecture, the physical architecture, and the allocated architecture. Now we're getting into this next area where we're defining the interfaces. So for an overview of this chapter characterizes the interfaces, discusses the functions associated with the interfaces, and looking at several contexts, communication systems and software design. And then it describes the interface architecture and discusses the interface design as it impacts system performance as a part of the design process. So I'll be injecting things from a couple different sources here in this chapter and some of the following chapters. And so one of the resources that I haven't leveraged too much up to this point is the NASA System Engineering Handbook, which is currently in the second edition at the time of recording this lecture. And so here will be an example of the kind of things that I want to be leveraging. So we're talking about interfaces. And so here we're seeing some different areas that we have external systems. And so that's definitely external to the types of system. And so the system consists of a ground system and a flight system. And so this would be what we would be considering for a scientific satellite mission. And the external systems would be the mission planning and the scientific community providing inputs and receiving input data back. Then we have the sensors that are actually collecting information for the mission. So just giving you a perspective on how that could look. From Moody and the textbook, here is that next step in this overall flow. And so we have been gradually going through this development arc, starting with the design problem, the functional, the physical, the operational, and now we're focusing on the interface architecture at this point. And so that's where we're at. And with this IDF0 diagram, we're trying to capture some of that development. Another way of looking at that is with a block definition diagram using SysML. And so we're having each one of those steps that is captured, and there's a lot of different references that are relevant. And so you can see that this kind of document, where this kind of SysML view, we're seeing a lot of different references that are coming into being used by this design. And this is showing evidence of the back end, the database of information that we're leveraging. And so just to maybe have that as a consideration, that we're not just creating a view, something that we can do with PowerPoint, but we're creating a database and then having various views, rendering that data in a certain fashion. Well, let's talk about the interface architectures. And so here we have a couple of points here, the message passing, the shared memory, and the network. So for message passing, the mail delivery that predictably occurs once or twice a day and allows those receiving the mail to turn their attention to the mail immediately or wait until a more opportune time. So this is the kind of thing where we would have with an interface is we need to have some mechanism for getting information in and out at certain times and certain modalities. For shared memory, a meeting or conference in which only one person speaks at a time and conveys relatively compact messages, all can hear that what is said, yet are restrained from other productive work during the meeting. So there's a corporate memory in that shared experience. And then a network, a telephone conversation that can involve messages of widely varying length can be instigated almost any time. So we can see mail or email. We can see about face-to-face or video telepresence as another form of an interface, and then as a network, having something like a telephone or instant messaging, where we have yet another way of having an interface and methods for communication. For message passing architecture, you want to allow the predictable exchange of information. You can have interrupt-driven communication. So this can be for operating systems. You can want to have a message that consists of a protocol, and we'll be talking about some details in terms of protocols. But here you're thinking about instruction, synchronization, and interrupt signals, and how that goes from data segments. And then there's the communication process that is followed. One node must win control of the communication channel, so it's given the go-ahead to communicate. The winning node becomes the master and sends a protocol segment to the intended receiving. So the communication process starts. Then the slave node notifies the master that the protocol segment was successfully received. So you have the transmitter, you have the receiver, and the master sends or receives the data segment to the slave, and the slave notifies the master the data segment was complete. So there's an agreement that, yes, we're ready to communicate. Then you actually have the communicate, and finally the master surrenders control of the communication channel. For asynchronous messaging, you can have messages can be stored in buffers, and send it and receive operations can be performed at the time as processing of the other task. And typically they are tightly coupled. So critical design factors include communication bandwidth and communication latencies. You want to get it there when you send it, and you need to have enough bandwidth and enough ability to bits per hertz to get all of the details passed in a timely fashion. For shared memory architectures, this is ideal for asynchronous communication request of a byte to a few words. You want to have a fast access storage device, typically a memory device, which is the interface among processors. And then you would have a communication process that would be different than what we talked about before. A processor generates a read or write request. The current owner of the variable is notified. The cache memory of the current owner is dumped. The global variables of the current owner are dumped to shared memory. The reader or write request of the processor is complete when the data is transferred. For shared memory, it can be a bus or a switch base. So there's various architectures that can be used. There can be contention for shared memory. So this is going to be a critical design issue. And for coherence, there could be multiple copies of the data drifting out of agreement. So that's another thing, that you have multiple copies. You want to make sure it gets to the end user, but you don't want it to be confused by having multiple copies getting through. So this type of a shared memory approach, it works well for highly parallel software applications. For network architecture, a distributed collection of shared memory systems in which each shared memory system has the ability to tap into the shared memory of the other system on the network. And that's what we would see in a network type of architecture. The main difference between the network and the messaging passing architecture is that the network provides demand-based service, while message passing primarily uses schedule transfers, and it can service hundreds of nodes. So there's a variety of different communication node architecture. You can have a master slave or a pipeline. You can have a bus. You can have a star or spoke, a ring, and a mesh. And so this is just an illustration of what those could conceptually look like when you have different elements of a system network together. So we'll have a handful of charts here now talking about standards of how we do that communication process. And so there are formal standards, say like the ISO or ITU or ANSI standards. There can be de jure standards that are mandated by legal authorities, and de facto standards which come into existence without formal process, but by popular use, it becomes a standard of practice. What are the benefits of standards? There's interchangeability, there's interoperability, portability, reduce cost and risk, and increased life cycle. So there's a lot of advantages for coming onto the bandwagon and dealing with and complying with the standards. You can interchange information readily. You can be interoperable, and so go to different parts of the network or different way that you might engage, and you know it's going to work. Systems can be moved and operated. It's going to help in terms of cost and risk reduction, that you're using the same protocols all over, and it's going to increase the life cycle when long-lived standards are adopted. So one type of architecture, a layering of communication, is the Open Systems Interconnect OSI architecture. And there's two parts of that: the four lower network layers, the physical, the data link, the network, and the transport, and then the higher, which is the session, presentation, and application. And so the software related control and engagements are typically more seen in the higher networks, and the hardware is more seen in the lower level, just to give some perspective. And so here we have the physical medium, and we can see how we have these various layers working through, going from a source to a destination. And so an application starts here and it drills all the way down to the physical level into the network. It only goes up to the network level, and then you get to the destination. You can go all the way back up to the application. So there's some more detailed charts here in terms of processing, of adding and stripping different types of information, the protocol control information and the interface control information, and then the payload, what actually you're trying to convey. And this course isn't on communication models, so I won't go over this in detail, but since we talked about the 7 layers of the OSI reference model, here are some more details that are available here in this lecture. They're available in the text and also the lecture notes. There's also the Common Object Repress Broker architecture. And this is a standard that would permit programmers to integrate software modules resident on the same network by treating each application as an object. So all 3 standards, the interface definition language, that's a formal standard. There's a CORBA. And so this treats a software application as object, and as such sits at the application level of the OSI 7-layer architecture, and it forms a client-server architecture. So this is what we were referring to on the last chart, that we're having this object request broker scenario, and it's actually occurring at the application level. There are various segments in CORBA. There's an interface definition language. There's an object request broker. And then you have these other things, the CORBA services, the CORBA facilities, and the CORBA domains. I'm just going to skip over this. I think we've covered enough detail to just give insight into this at a top-level survey point of view. This is just an illustration of what that would look like for ORB interactions with clients and servers. And then we have the services in the ORB object services architecture. And once again, I'm not going to go through this, but this is available if you wanted to go into this in more detail. So this whole chapter is focusing on interface design. And so here are some of the major elements and things below that. You want to define the interface requirements. You want to set a high-level interface architecture, develop a functional architecture, develop a physical architecture, develop an allocated architecture, and add functions to components connected to the interface as needed. So a lot of these steps are things that we've already spoken about, but we're applying it towards the interface specifically, and there's a lot of next level detail below those that are also need to be addressed as we're doing the interface to design process. And so you could be using this as a cookbook for how you're going to go about designing an interface. So we come back to the elevator example, and we can be thinking in terms of the interfaces there. We need to define the interface requirements. I think we've been over this enough now that we're starting to get an idea how it needs to operate and the kind of exchanges of information and things that need to take place. Emergency communication, passenger encounter emergencies, want to be able to do things related to a number of different types of things in terms of that would be addressed in the interface. You want to select a high-level interface architecture of the interface. So you can, by identifying several options, define the trial interface for each, evaluate the alternatives, and then choose the best one. So next, you want to develop the functional architecture of the interface, the physical architecture, the allocated architecture, and the function to component connections. And what it is saying here is it's not needed because this interface is standard. So if we're using something that is a standard convention, then this would simplify this overall, but you can still check the box that says that we did this. And for this last one as well, it also has that same type of caveat that it's not needed because the interface is standard. All right, well, that's a quick synopsis going through the interface design, and we'll end it there. Thank you.